What's up, guys? This is Irene Aldridge, and today we're going to talk about SVD, which is singular value decomposition, and its cousin PCA, principal component analysis. Now, a lot of you may be rolling your eyes right now and saying, oh my goodness, not the SVD and PCA again. But the truth is, as we show in our new book, Big Data Science, SVD and PCA are the optimal methodologies for doing big data. They're way better than doing machine learning. Many machine learning techniques are susceptible to overfitting. Big data, SVD and PCA are a lot better at handling overfitting than things like neural networks, for example. And the reason for that is because SVD and PCA deliver optimal decomposition. And you can see again the proof in our book. I'm not going to talk about the proof today. What I'm going to do today is really show you what that means. So how it optimally works with data and what does it do. So in traditional analysis, there's a researcher who is like you, and that researcher has to come up with a hypothesis. And this is something that a lot of PhD students have struggled over the years, like, where do I get my idea? How do I get this hypothesis to work? What kind of idea do I need to come up with? And the traditional response is, oh, you have to read a lot of literature because, this is where the ideas come from, et cetera, et cetera. So what you end up is a lot of repetitive ideas, really, that reinforce potential biases or reinforce our opinions that may not necessarily be reflective of the true reality that's out there. So to get to the true reality, SVD or PCA are the tools, because what these tools are doing, they're taking your data and then they're finding the optimal factors in your data without your interference. So they're doing it using what's called eigenvectors and eigenvalues, and eigen in German means intrinsic. So these are the factors that are intrinsic to the data itself. Okay, and as we show in our book, you can prove that these factors are absolutely optimal. So these are the factors that you're supposed to be working with. You don't even need to dream up any other factors. Okay, and the added bonus is these factors are linear. So your data is related to them linear. So there is lower risk of overfitting as compared to nonlinear models where you torture the data to the point where it finally fits, but then of course it doesn't fit out of sample. So what I'm going to show you is an application that we have on our website. I'm going to share my screen now. As you know, we have a book website called bigdataFinanceBook.com, and we're going to share the screen. Okay, okay, here we go. All right, so first I'm going to show you the code. Okay, so there's a code on our website. Again, it's bigdataFinanceBook.com. And under the section code, if you go to chapter 5, you have to sign up first for the website. But here's the code of how to implement what I'm going to show you next. Okay, and this is what I'm going to show you next. This is, you don't need to sign up. You just go to our website and then you type /eigenportraits. Okay, and for eigenvalues and portraits for portraits, because the easiest way to illustrate the power of SVD and PCA is really to look at the image decomposition. So here's, we have an image, which is a meme. I have been collecting different memes for a while related to AI. But here's Captain, I forgot what his name is, and he's saying artificial intelligence. All right, so we're going to use SVD to actually decompose this image. Okay, so this image right now contains 550 columns. After we decompose it, we get what's called a scree plot of singular values. Again, it's all described in detail in chapter 5 in our book. Okay. But this is the summary of basically different components that comprise this image, and what these components are, ultimately they represent linear combinations of our columns. Okay, so you can think of this image as a two-dimensional data set. So you have 500 columns, and I don't know how many rows there are, less than 500 in this case. Okay, so and the interesting part is each column is like a column on a table, right? Because it's a two-dimensional image. So and each value, like each pixel, represents a value too. It represents in grayscale, it represents a color, right, from 0 to 155. where 0 is black, 255 is white. So anyway, so if we take only the first of 5 of these principal components, what we get is this image here, which is barely intelligible. Okay, so there's something there, but not really. If we go to 20 right here, we're already getting an image that we can see. And if we use what's called Marchenko-Pasteur limits, which are optimal ways of determining the number of important eigenvalues that we should take into account. In this case, for this image, it's 73. We discussed Marchenko-Pasteur in chapter 7 of our book as well. So, and how to compute it. But you can see that with Marchenko-Pasteur optimality, we're already getting basically the entire image very, very crisp. Okay, and that's the whole point. So what I want you to do here, what I'm showing you this for, you can do this for any kind of image. So for example, I have a different image, which is actually the 3 covers of my books. I have more books, by the way, but these are some of the books that I've written. Okay, so and now we're going to process them, and we're doing the same thing. Okay, so these are the 3 covers. Now there are 495 columns. The optimal number of columns now, according to Marchenko-Pasteur, is only 63. This is the scree plot. It's a lot more kind of looking like a right angle. Here's again reconstruction with 5 principal components, reconstruction with 20 principal components, and the reconstruction with 63 principal components, which produces the best results, almost very close to the original. The color is messed up. I mean, it's doing it in grayscale, but this is really to show how you can reproduce the content using just so many factors. Now, what does this have to do with finance? Well, as I'll show you, as we show in the book, okay, also in chapter 5 and chapter 6, you can build really, really solid portfolios that are consistent with a bunch of traditional metrics like CAPM and the Ross's APT, because they're linear factor, basically linear factor models where the factors are optimally determined by big data. Okay, and in that case, you're producing just much more sound outcomes than if you took some factors and you guessed which one goes where, and then you just tortured the data until it fit. So bottom line is, this is a superior method, unsupervised learning, and this belongs to the unsupervised learning. It's a very, very solid idea, the true artificial intelligence that people are referring to, and something that's here to stay. And I hope you check it out. Also, don't forget to download the code. It's all available for you there. And I'll see you soon. Thank you and have a great day.